Welcome to all for the course CS407 Machine Learning Module 2 Part 2. Part 1 we already covered in the previous video. Myself, Meherban Amas, Assistant Professor, Rajagiri School of Engineering and Technology, Department of Computer Science. Let's see what is meant by dimensionality reduction. So dimensionality reduction is the process of reducing the number of variables under considerations and by obtaining a smaller set of principal variables. And the smaller sets of that corresponding variables are called the principal components, and the dimensionality reduction may be implemented in two ways. One is called feature selection and second one is feature extraction. Let's see more details about dimensionality reduction. So first one, in the previous slide I am already explained the dimensionality reduction can be achieved in two ways. One is called feature selection and second one is feature extraction. So let's see what is meant by feature selection. In feature selection, so we are interested to finding a total of n features. Out of that we are finding a k. So that gives the most information and we discard other n minus k dimension. Example called subset selection method. So consider one example for determining the CGPA of a student. So we need the past history like the previous semester CGPA and academic performance, but we don't require any personal details for calculating the CGPA. So we can eliminate certain features like a personal informations like age and all. So this is called feature selection. So we are finding a specific set out of n features. Second one is feature extraction. Interested in finding a new set of k features that are a combination of original n features. So in this method, the main examples are one is called PCA and second one is linear discriminant analysis, is also called LDA, and PCA stands for principal component analysis, and more details about PCA will discuss in the coming slide. In this slide, I am going to explain why we need a dimensionality reduction. So of course, the dimensionality reduction will help to reduce the memory and computation. And sometimes when an input is decided to be unnecessary, we save the cost of extracting it. And simpler models are more robust on small set. And when the data can be explained with fewer features, we get a better idea about the process that underlays the data, so which allows a knowledge extraction. So in this slide, I am going to explain what is meant by subset selection. The process of selecting a subset of relevant features, it can be variables and predictors, for use in model construction. The feature selection techniques are used for four reasons. So first one, it reduces the complexity of the model. Second one, it enables the machine learning algorithm to train faster. And third one, it improves the accuracy of a model and if the right subset is chosen. And the last one, it reduces overfitting. So what is meant by overfitting, we already discussed in module 2 part 1 video. So overfitting means certain machine learning algorithm will perform better during the training, but when we do a testing, the algorithm don't work well. So if we have a good features, then it can be avoid overfitting. So consider a simple example. Suppose we need to classify the fruits are passing on a conveyor belt and we need to classify whether it is an apple or a fruit, apple or orange. So in that case we need to extract some features, and most probably we are selecting the features like a color and the shape and all. So from the color itself we can determine whether it is an apple or an orange. In this slide, I'm going to explain what is meant by subset selection. The feature selection techniques is used when the data contains many features that are either redundant or irrelevant. So at that time we can remove that information without incurring much loss of information. So there are two methods, forward selection and backward selections are the two feature selection approaches. So what is meant by forward selection? In forward selection, we start with no variables and add them one by one. And each step adding the one that decreases the error the most until any further addition does not decreases the error. So I will explain the forward selection with the help of an algorithm in the next slide. So consider the algorithm for forward selection. So we use the following notation. N is the number of input variables and x1, xn are the input variables. The input variables means during the classification, the regression and all, this input variables which are represented as a features, and fi is the subset of set of input variable. And E of f of I is the error incurred on the validation sample when only the input in fi are used. So most machine learning algorithm, we divide the training data set into the entire data set into the training, testing and for the validation also. So in order to measure the performance and all, sometimes we require a validation data set also. So error of f of I means we have the predicted value and actual value and we calculated the difference. So that indicate the error of fi. So in initial case, we can start the subset of set of input variable as null and the error is empty. And repeat the following and until the error of the next one which is greater than or equal to the error of the previous one, that is fi plus 1 and fi. So for all possible input variable, we need to train the model with the input variable and calculate the error on the validation set. And choose that input variable that caused the least error, and m is equal to argument minimum of e of fi union xj. So we need to include that variable. And the next set of features, as I already explained, fi is the subset of the set of input variable. That means it is a collection of features. And the next one is the previous one, union the x of m. X of m means the lowest error value. That feature is, while we using, we get a least error value. So we can add that feature into the fi plus 1 set. And the set fi is outputted as the best subset. So after applying the algorithm, we'll get the best features. The best features means the best input variables. I hope the algorithm part is clear. So in this slide, I'm going to explain more details about backward selection. In sequential backward selection, we start with the set contain all features. In the previous one, we started from empty, but it's just reverse of that. We need to start with the set containing all the features and at each step remove the one feature that causes the least error. In this slide, I'm going to explain what is meant by backward selection. And we use the same notation. N is the number of input variable, x1, x2, xn are the input variables, f of I is the subset of the set of input variables, that means it is a feature set, and E of f of I is the error incurred on the validation sample when only the inputs in fi are used. So earlier one we have started from the initial feature as null set, but here it is the set of features. That is why here it is written as x1 up to xn. and the starting error is a infinity as in the previous case. And here we need to repeat the following step until the error of the previous one, which is greater than the current iteration. So here we need to train the model with the input variable fi minus xj, because we need to exclude that, okay, and calculate the error on the validation set. And choose that input variable that caused the least error. Okay, so we need to calculate the error function and we need to take the minimum value. And in the set fi plus 1, we are eliminating the corresponding the value of xm. Okay, so here we are eliminating it. In the previous one, we are adding. So the set fi is outputted as the best subset. In this slide, I am going to explain principal component analysis. The short form is PCA. Let's see some of the basics for PCA. Before discussing more details about PCA, we need the basic definitions of different statistical parameters. So first one, what is meant by statistics? So statistics is analyzing the data sets in terms of the relationships between the individual points. So what is meant by standard deviation? So standard deviation is the measure of the spread of the data. And the calculation of standard deviation can be done by taking the average distance from the mean of the data. In this slide, I am going to explain what is meant by variance. Variance is another measure of the spread of the data in a data set. So the calculation can be done the variance of x, which is equal to the expectation of x minus mu the whole square. So one simple question, why have both variance and standard deviation to calculate the spread of the data? Just think about it. Because the variance is claimed to be the original statistical measure of the spread of the data. However, its a unit would be expressed as a square, so which is unrealistic to express the heights or other measures. Hence, standard deviation is the square root of the variance. So that is why we are using both variance and standard deviation to calculate the spread of the data. The next important term is covariance. What is meant by variance? Variance is the measure of the deviation from the mean for points in one dimension. And covariance is a measure of how much each of the dimensions vary from the mean with respect to each other. The calculation of variance and covariance will discuss in PCA part. The covariance is measured between two dimensions to see if there is a relationship between the two dimensions. Example, the number of hours studied and marks obtained. The covariance between one dimension and itself is a variance. Next is what is meant by covariance matrix. Representing the covariance between the dimension as a matrix for three dimensions. So consider this example. This is a three-dimensional matrix and we are calculating the covariance between the three variables xx, xy, xz, then yx, yy, yz, zx, z by zz. The diagonal is the variance of x, y and z. So covariance of xy, which is equal to covariance of y comma x. That means it is a symmetric. And the n-dimensional data will result in n-into-n covariance matrix. Next is what is the impact of the positive covariance and the negative covariance. So a positive value of covariance indicates both dimension increases or decrease together. Example, as the number of hours studied increases, then of course the marks in that subject increases. Another example is negative value indicates while one increases the other, then the other one is decreases or vice versa. Example, the active social life at RSET versus the performance in CS department. So if covariance is 0, the two dimensions are independent of each other. Example, the heights of a student versus the marks obtained in the subject. In this slide, I am going to explain how we can represent a transformation matrices. Consider a matrix 2, 3, 2, 1 multiplied by 3, 2, which can be represented as 12, 8. So, which is also represented as by multiplying a constant with a simplified matrix. So, which is equal to 4 into 3, 2. So, in this slide, the continuation of the transformation matrices. Consider a vector 3, 2, and when we multiply it by a scale factor 2, you will get 6, 4. So, multiplied by the square transformation matrix, we see the result is still a multiple of 4. Why? Because we already know that the vector is a contain both length and direction. So, scaling a vector only changes its length and not its direction. This is an important observation in the transformation of matrices leading to formation of eigenvectors and eigenvalues. So, what is meant by eigenvalues and eigenvectors will explain in the further slide. Next is what is meant by eigenvalue. So, eigenvalue problem is any problem having the following form: S into V, which is equal to lambda into V, where lambda is a scalar and V is the non-zero vector and S is the n into n matrix. Any value of lambda for which this equation has a solution is called the eigenvalues of S, and the vector V which correspond to this value is called the eigenvectors of S. So, any problem you can formulate in the form S dot V, which is equal to lambda V, and here the V value which corresponds to this value is called the eigenvectors of S, and the any value of lambda for which this equation has a solution is called eigenvalue. And eigenvalue and eigenvectors are very important while you doing a problem in PCA. Slide, I am going to explain how to calculate an eigenvalue. So, consider a matrix 2, 3, 2, 1, V is the 3, 2, and which can be represented as 4 into 3, 2. So, this matrix can be in the form S into V, which is equal to lambda V. So, therefore, 3, 2 is an eigenvectors of the square matrix S and 4 is an eigenvalue of S. So, in this slide, I will explain how to calculate eigenvectors and eigenvalue. Consider S dot V, which is equal to lambda V, which can be rewritten as S dot V minus lambda into I dot V, which is equal to 0. So, V is the original matrix and I is the identity matrix. And you can rewrite the expression S minus lambda I dot V is equal to 0. And find the roots S minus lambda I will give the eigenvalues, and for each of these eigenvalues there will be an eigenvector. And how to calculate eigenvalues and eigenvector will explain in the coming slide. Let's see a simple example how we can calculate eigenvalues and eigenvector. Consider a matrix S is equal to 0, 1, minus 2, minus 3. And you can rewrite the expression S minus lambda into inverse matrix, which is equal to 0. And you will get a quadratic equation lambda square plus 3 lambda plus 2, which is equal to 0. And while you solve this equation, you will get two lambda values, lambda 1 which is equal to minus 1, lambda 2 which is equal to minus 2. So these are two eigenvalues. Next is properties of eigenvectors and eigenvalues. Note that irrespective of how much we scale, the solution is always a multiple of 4, as we already explained. The eigenvectors can only be found for square matrices and not for every square matrix has eigenvectors. Given an n into n matrix, we can find n eigenvectors. Let's see what is meant by principal component analysis. So, principal component analysis is a technique that can be used to simplify a data set, and it is a linear transformation that chooses a new coordinate system for the data set such that The greatest variance by any projection of the data set comes to lie on the first axis. That is called the first principal component. And the second greatest variance are called the second principal component. So our aim is to retain the highest principal component and eliminate the later principal component. So PCA can be used for reducing dimensionality by eliminating the later principal components. So in this principal component analysis, from this diagram, these are the direction where there is most variance and the directions where the data is most spread out. So that we can see in this figure. In order to find the direction where there is most variance, we need to find the straight lines where the data is most spread out when projected it, and the vertical straight line with the points projected on it, and it will look like this. From this diagram, you can clear on this line the data is way more spread out. That means it has larger variance. But in fact, there is not a straight line you can draw that has a larger variance than the horizontal one. So this horizontal line is therefore the principal component because the remaining lines do not have a much variance or more variance compared to the horizontal line. So that line indicates the principal component. And this is a scatter plot for PCA. You can see in x-axis and y-axis we are representing the different features, and from this we can find the principal components. Let's see a scatter diagram and the spread along x direction, spread along y direction, and the largest spread, the largest line you can draw it, so that indicate the greatest spread you can find it. The direction of largest spread. The direction of the first principal component, that means the solid dot, is the point whose coordinates are the mean of x and y. The second diagram indicates the direction of the principal component, and the third diagram indicates that the principal component vectors. So vectors are the unit vector in the direction of the principal component. Next is the different steps for PCA. First of all, standardize the data. Second one, calculate the covariance matrix. Third one, find the eigenvalues and eigenvectors of the covariance matrix. Finally, plot the eigenvectors or principal components over the scaled data. So let's see how we can represent an equation for a principal component findings. Consider, as I already explained, AV which is equal to lambda V. And in this diagram you can see x and the corresponding y and the lambda x and the lambda y. And this is an original matrix 2, 3, 2, 1 multiplied by 3, 2 and by a factor 4 which is multiplied by 3 and 2. By finding the eigenvalues and eigenvectors of a covariance matrix, we find that the eigenvectors with the largest eigenvalues correspond to the dimensions that have the strongest correlation in the data set. And this is the principal component. Let's see some of the applications of PCA in real life. Face recognition, image compression, pattern finding, gene expression analysis, data reduction, data classification, trend analysis, factor analysis, and node. Let's see the different steps in PCA. First one, the data. So we consider a data set having n features of variables, and if we have n examples, and let the value of the ith features x1, x2, xy, xn. Next step is compute the mean of the variable. So we already know how we can compute mean. So mean can be calculated as xi bar, which is equal to the total number of samples into xi1 plus xi2 plus xin. So PCA processes subtract the mean from each of the data dimension. All the x values have x subtracted. This procedure, a data set whose mean is 0. Subtracting the mean makes variance and covariance calculation easier. The variance and covariance values are not affected by the mean value. Let's see how you can find the covariance matrix. Consider the variable xi, xj, and the covariance of the ordered pair is defined as the covariance of xi, xj, which is equal to 1 by n minus 1 into sigma k is equal to 1 to n xik minus xi bar into xjk minus xj bar. And we calculate the following n into n matrix as called the covariance matrix of the data. And the covariance matrix, which can be defined as S is equal to covariance of x1 x1, x1 x2, xn xn, then covariance of xn x1, xn x2 and xn xn. The covariance matrix calculation is to determine how the variables of input data set vary or to find the relationship between them. So next is how we can calculate the eigenvalues and eigenvectors of the covariance matrix. Consider S be the covariance matrix and I be the identity matrix. So set up the equation, the determinant of S minus lambda I, which is equal to 0. And it has n real roots, and these roots are the eigenvalues of S. If the lambda value, which is equal to lambda dash, is an eigenvalue, then the corresponding eigenvector is a vector u, which can be given as u1, u2, un. S minus lambda dash into I of the matrix, which is equal to 0. We now normalize the eigenvectors. Given any vector x, we normalize it by dividing x by its length. The length of the vector, which can be given as x is equal to x1, x2, xn, and is defined as the modulus of x, which is equal to the square root of x1 square plus s2 square plus xn square. And given any vector u, the corresponding normalized eigenvector is computed as 1 by modulus of u into u. And we compute n normalized eigenvectors, which can be given as ei is equal to 1 by modulus of ui into ui, where I is equal to 1, 2, n. We now normalize the eigenvectors. Given any vector x, we normalize it by dividing x by its length. The length of the vector, which can be given as x is equal to x1, x2, xn, and is defined as the modulus of x, which is equal to the square root of x1 square plus s2 square plus xn square. And given any vector u, the corresponding normalized eigenvector is computed as 1 by modulus of u into u. And we compute n normalized eigenvectors, which can be given as ei is equal to 1 by modulus of ui into ui, where I is equal to 1, 2, n. Next is how we can derive a new data set. Order the eigenvalues that we already got from highest to lowest. And the unit eigenvector corresponding to the largest eigenvalue is the first principal component. And the unit eigenvector corresponding to the next highest eigenvalue is the second principal component. So let the eigenvalues in the descending order and let the corresponding unit eigenvectors e1, e2, en. And choose a positive integer such that 1 less than or equal to p less than or equal to n. And choose the eigenvectors corresponding to the eigenvalues lambda 1, lambda 2, lambda p. And form the matrix E1 of t, E2 of t, EP of t, where t is the superscript denote the transpose. After that, we need to find another matrix, form the following n into n matrix, that each variable is subtracted by the mean value. Next, compute the matrix x nu, which is equal to f of x. And this gives us a data set of n samples having the p features. So after that, we need to form a new data set The matrix X new is the new data set, and each row of this matrix represents the value of a feature. So conclusion is, this is how the principal component analysis helps us in dimensional reduction of the data set. Note that this is not possible to get back the original n-dimensional data set from the new data set. Thank you all. So this we come to an end of module 2 in machine learning, and in this video we covered the PCA, that is principal component analysis in more detail, and the algorithms of PCA and forward selection and backward elimination. Thank you all. Thank you so much.